Greetings to all. I'm Sona Stiju from Model Engineering College, APJ Abdul Kalam Technological University, Kerala, India. I'm here to present my paper, Footstep Power Generation. Electricity has now become a lifeline for the human population, with demand increasing by the day. The growing worry about the demand-supply gap for power has heightened the interest in research of alternative energy sources and their sustainable use. This is where the concept of energy harvesting comes into importance. Energy harvesting is capturing energy that is already available, but will go in waste if not used. The objective of our project, Footstep Power Generation, is to harvest energy by the means of a non-conventional energy source. We suggest a method for power generation by utilizing piezoelectric sensors. When pressure is applied to these sensors, an alternating voltage is produced across them. The voltage produced is proportional to the rate of change of applied pressure. The proposal to use the lost energy from human locomotion to generate power is especially relevant and crucial for highly populated nations like India and China, where people's mobility will be a boon in producing electricity from their own footsteps. Electrical power generation via piezoelectricity is one such energy harvesting approach that does not negatively impact the environment. This is carried out by the principle called the piezoelectric effect. The piezoelectric energy harvesting converts the mechanical energy into electrical energy and can power low-power electronics. They provide a way to harness wasted energy without negatively impacting the environment. The novelty of this project is that the project is using piezoelectric crystals. This brings a novel and innovative approach to sustainable energy production. It presents an exciting and groundbreaking approach to address the world's energy need by tapping into the kinetic energy produced by the human footsteps. This project can harness an underutilized and often overlooked energy source. The utilization of piezoelectric crystals, which convert the mechanical pressure into electrical energy, offers a unique and efficient way of energy conversion. System overview. The components used in this project are piezoelectric sensors, 27 mm diameter, 2200 microfarad, 16-volt capacitors, bridge rectifier ICs, IN4007 diode. In order to enhance the output power efficiency, non-electrical components like sponges and silicon bumpers are used. Block diagram. The block diagram shows us the conversion of the energy and storage of the final output voltage. The core component of the system, piezoelectric sensors, are strategically placed in areas where the foot traffic is significant. When subjected to pressure or stress, the piezoelectric materials generate an electric charge across their surfaces proportional to the applied force. The piezoelectric sensors are deployed in designated areas to detect the footstep and convert the energy as per the requirement. Bridge rectifier. The bridge rectifier transforms and stabilizes the output from a pulsating AC to a DC form. It ensures that current flows in a single direction, eliminating negative half cycles and providing a stable DC waveform. The backflow current prevention is done by IN4007. This is a standard rectifier diode that allows current to flow in one direction while blocking the flow in the opposite direction. The high backward resistance of the IN4007 diode makes it suitable for backflow current protection in the circuit. The generated voltage is stored either in a capacitor or a battery. This is used to store the energy that is of excess for later use or to maintain a constant power supply. The rectified DC voltage output of the bridge rectifier is connected to the capacitor. It charges and retains the electrical energy generated by the piezoelectric sensors. It smoothens the DC waveform, eliminating voltage fluctuations and delivering a more steady output. The implementation is done as follows. As people walk over the sensors, their weight exerts pressure on them, causing the piezoelectric crystals to deform and generate an alternating voltage. To convert the alternating voltage into DC voltage, a bridge circuit is utilized. The bridge circuit consists of diodes and resistors arranged in a specific configuration. This rectifies the alternating voltage, converting it into a unidirectional flow of current, thereby generating the required DC voltage. To prevent the backflow of the current and ensure a one-way flow, a diode is placed after the series parallel combination of the sensors. This diode acts as a check valve, allowing the current to flow in one direction while blocking any reverse flow. The output DC voltage that is being obtained is then stored in a capacitor. The capacitor serves as an energy storage device, allowing the system to store and accumulate the generated electrical energy over time. This stored energy can then be used to power various low energy devices and can further be distributed to other applications. This is the circuit diagram. Here we can see that 50 sensors have been used, out of which 44 of them are being connected in parallel, whereas 6 of them are connected in series. A small-scale representation of our project is implemented through this prototype. This design involves arranging piezoelectric sensors in a series parallel configuration, with 6 sensors connected in series and 44 of them connected in parallel. The piezos are mounted between 2 wooden boards and bolted with 4 screws, one at each corner with a spring placed on each screw. Each piezoelectric sensor is positioned on a sponge and equipped with a silicon bumper mounted on top. Observations. After the assembly, we move into the testing process of the project. Our project has a combination of 50 piezoelectric sensors, and the series parallel configuration of 6 in series and the rest in parallel ensured that we have the highest output efficiency. The voltages formed across the piezoelectric effect as well as the quantity of current that passed through them were measured. Different values of weight ranging from 20 kilograms to 80 kilograms were tested. The voltages, the stresses, and the different pressures were evaluated and observations were taken. So this is the observation table with our inference, and the graph for power with respective voltage generated is plotted as follows. Results. After conducting thorough research on various types of piezoelectric sensors available in the market, we determined that a 27 millimeter diameter sensor was more suitable for our project as compared to the 21 millimeter diameter sensor. To optimize power generation, we conducted experiments with different series and parallel connections of sensors. At first, we used a bridge of IN 4007 diodes for full wave rectification in our circuit. And on further research, we found that the power consumption was considerably less for MB10 bridge rectifier IC.
Breakthrough in the project.
During our extensive research, we made a significant breakthrough by discovering that bending the sensor slightly rather than applying direct pressure resulted in increased power output. This phenomenon occurs because bending the piezoelectric sensors not only applies stress, but also takes into account the strain on the sensor, resulting in higher voltage production compared to a single sensor. This breakthrough was the missing piece of puzzle for our project. In order to achieve the desired bending effect without damaging the sensors, we introduced the use of a sponge beneath each sensor and a silicon bumper on top. These additional components allowed us to achieve the desired bending effect without compromising the integrity of the sensors. Future scope. As the consumption of energy grows, population depends more and more on fossil fuels such as coal, oil, and gas day by day. There is a need to secure the energy supply for the future due to the price hike as well as the growing depletion rate of these fuels. This is where the importance of non-conventional energy sources comes into play. For densely populated nations such as India and China, where roads, railway stations, bus stops, temples, and other public places are overcrowded With millions of people constantly moving around, this project may help to harness the energy lost through our footstep, which can then be put to good use. The proposal for utilization of power generation via human locomotions is very relevant and important. Footstep power generation captures energy from human footsteps to create renewable electricity readily available in public places and high traffic areas. This innovative approach efficiently taps into underutilized energy that would otherwise go in waste, contributing to a cleaner and more sustainable energy mix. This project reduces carbon emission and our reliance on fossil fuels, making it a smart and eco-friendly way to power our world. The project is a well-balanced energy generation concept that is simple to set up and implement. If implemented on a large scale, this concept can be used as an alternative source of power. This can also be effectively used in overcrowded areas such as roadways, railway stations, and other public avenues where millions walk around all the time. These are the most important references for our project.
Thank you.